Hello everyone. I am Tamogno. So, I just wanted to give you guys a little tutorial so that the concepts of like why a neural network is used may be a little bit clearer to you. So, the website I'm using here is Neural Network Playground, and so let's just start. Okay. So right now we just have two features, two input features, x1 and x2, and then a single hidden layer with three neurons, right? And then we are feeding it directly into the output. And this is the data set that we have. So the task is that we have to perform binary classification between the orange classes and the blue classes, right? And we need to accurately predict whether any new sample belongs to the orange class or to the blue class. Okay. So now let's try to train this, right? So we feed these features into this, and there's linear combinations formed at each of these neurons, and then those are passed into the output. So right now I'm using a linear activation, which means that these linear combinations are directly being fed to the output instead of passing through a non-linear activation function. Okay, so let's try training, right? So you can see that the decision boundary, which is marked by this line between this white line between the orange and the blue regions, this shifted. So these parameters are have been tuned. So you can see that well, like it has been tuned so that your decision boundary is in the middle of these two regions, right? So this enables you to accurately classify both, and you can see here that test loss and training loss are both zero because every point is perfectly classified. Okay, so you can also look at what linear transformations each of the neurons learned by hovering over this region. So you can see that this is a linear transformation, this is also a linear transformation, and this is also a linear transformation. So individually all three are learning linear transformations, and then what you have at the output is just like another linear combination of these three lines. So that is since the linear combinations of lines are linear as well, so finally at the output we have a linear classifier. Now let's see, let's try to do this for a different data set, right? So let's try to do this for this data set. So okay, I want to experiment with one other thing. I have no idea how this will go, but let's see. So if I reduce this to a single neuron, right, and then try training. So since this is still a single transform, a single linear transformation, a single linear boundary can separate the orange and blue classes. So it still works, right? And you can see that this transformation is pretty much what is used in, but I believe that it is just inverted here. So this weight is -1. Yeah. So you can see that, right? So this is the transformation, and then this is just inverted by -1 to get this final value, right? So you can see that since the data here was linear, so just a single line is good enough to uh, like classify these. So in effect, what I have now is just a linear classifier, if you think about it, because there is W1 x1 plus W2 x2 plus maybe some bias, and that translates to a single line, right? So that is this essentially boils down to a single linear classifier. Okay, so I just wanted to start with that insight in mind. And now let's see if we try this linear classifier on a more complex data set. What is going to happen? You can see that it still tries to fit a transformation to the middle of this data because it sees that blue are on one side and orange are on another side, but it can still fit only these transformations, right? So this is the maximum it can do at a single neuron because this is still a linear classifier. Now, what if I added more hidden layers? Now, what is going to happen? You can see that I still end up with the same like line. The reason is that even though there are now three linear transformations that are being learned, and you can see that individually these three are different, but when these are combined, since I'm combining linear transformations, then the resulting transformation is still a linear thing. So even though I have three neurons here, without the presence of any activation function, this is still effectively a linear classifier. And as you can see, that this data is clearly not linear. So a linear classifier will not be able to do well on this task, as is also reflected by the test loss and training loss. Okay, so now how can we do better, right? So now we come to the first key thing of neural network, which is the activation function. So you can see that here we have multiple options for the activation function. Now, instead of linear for a binary classification problem, let's shift to sigmoid. Okay, now let's see if that changes our decision boundary, right? So you can see that it took some time, but eventually it was able to learn this data well, right? So the test loss and training loss are both quite less, right? So you can see that because I added some non-linearity in the form of this activation function, now I can allow my classifier to learn non-linear data as well, which was not possible earlier with just linear classifiers. Something to note is that individually at these neurons, each of these transformations is still linear, but the activation function is applied after each of these linear transformations, so the resulting effect is non-linear. Okay, so this tells us the use of activation functions. Now you can see that this took roughly 270 epochs to fit the data well. Now let's see if I use ReLU for the same thing. Then you can see that not only am I able to fit it to the data in fewer number of epochs, but you can also see that the a decision boundary looks like it is made up of different line segments, right? That is a function of like the nature of the ReLU function. Since the ReLU function is essentially omitting some part of the transformation and only transmitting some part, so in effect, it is like a piecewise linear transformation. So whatever resultant boundary I will have, which is the summation of all these three boundaries, is also going to look linear in some segments. So it's not a single line going through the entire data set, but it's like a combination of a few lines going here and there, right? So now if we have understood this well, so then let's whereas for the sigmoid activation function, you could see that since the sigmoid activation function has a curved area in the middle, so this uh, region boundary also looks curved. Okay, so this basically tells us the importance of different activation functions. Now, something else I wanted to cover is let's see if we have more hidden layers, right? So then can we learn this data set through this? So you can see that training is slower now, right? Because I have to tune more and more parameters. So earlier I only had three parameters, but now I have five parameters to train, apart from the biases, of course. So it is taking longer to train. So it was still able to do well on this, but it took 745 epochs. Now let's see if Relay is able to do this faster. Yeah, so it does it much faster, right? So you can see that ReLU is much faster converging than Sigmoid in terms of an activation function. So, and you can still see this kind of piecewise linear or like segmented linear activation, like sorry, decision boundary here. Okay, so yeah, so that is another thing to consider. Now, let's say if I went back to the single layer configuration and instead I had a more complicated data set like this. Now let's see how well we can do, right? So you can see that it's pretty much fixed at this point and it cannot do any better than this, right? So then what is the way out, right? So there are three linear transformations which we are learning and then we are combining them through ReLU. So you can see that through this piecewise linear boundary. But then this is still not good enough, right? So clearly we need to learn a lot more variations within the data, and we also need more nonlinear decision boundaries, right? So in order to add nonlinearity to the learning, I would like to add hidden layers. So now let's see if this improves. So you can see that now there is more nonlinearity in this, and you can see that if I let it run, then it is doing a slightly better job here at classifying the blue points, right? So the test loss is like 40%. Okay, now if I was adding neurons here and here, now let's see what happens. So it's not immediately apparent, but you can see that the test loss and training loss are much lesser than before. But there is also a lot of variation in this due to certain weights being exceedingly high and certain weights being exceedingly low. So let's try another alternative strategy. So what if we add another set of hidden layers? Okay, so this doesn't necessarily work well. So again, like it's not guaranteed that a certain configuration will work well, but roughly these are the effects of what we do, right? Yeah, so that is a lot of the things I wanted to cover. There's one other thing. So you can see now that the weights are shown by the thickness of the lines. Here, some of the lines are pretty thick. You can see that the weights are pretty high. Okay. Now, if I add regularization, so if I add L1 regularization, so let's get back to the original configuration with four neurons. Then you can see that now each of these lines appears less thicker than it was, right? Earlier. Let's do 1000 epochs. So our test loss is like 16-17%. But I mean, yeah, so the weights appear slightly lesser than that, right? There is no weight which is 4 in magnitude. These are like still 2.1 and 1.3, and like this is what. So regularization essentially adds a penalty for having any large weights, which means that, oh, sorry, the regulation rate was smaller, I guess. So that's probably why. So let's see, I add a regulation of zero point 0.1. So you can see that training is almost stopped because like the regulation rate is too high. Let's try something like 0.01. So now it is learning, but because of this small weights, it is not able to learn. So let's try reducing the regularization rate even lesser. So this is doing slightly better, but you can see that while each weight is like much smaller than it initially was, but that doesn't mean that I can necessarily learn the transformation better, right? So like while regularization helps you keep the weights within certain ranges, but it may end up slowing your learning, or it may end up allowing you to not learn the transformation at all. Okay. Now if you add L2, then you'll penalize the weights even further. And what that means is each weight will now be like even smaller than earlier. But for at least for this case, it seems to work slightly better than the previous case. So there is also some experimentation involved. Now, let me see. So yeah, so like now if I remove the regularization, and then I see the effect of learning rate here, right? So you can see that in the default configuration, this changes a little slowly, let's say, and within 1000 epochs, it maybe saturates at this value. Now, if I increase the learning rate, then you will see what happens. So you can see that the transformation shifts much faster than it was earlier, and you can see that the output is much noisier than it was before. So like if you're adding if you're increasing the learning rate, then that means that you are increasing the amount by which each weight gets updated within each epoch, and that means that you will end up with like more variations, right? So this may be a good thing or maybe a bad thing in certain cases. So yeah, these are mostly what I wanted to cover. The last thing is, okay, what if I can go back to a linear transformation and then a single hidden layer with a single linear classifier. So this is now we are back to the linear classifier. But what if we still wanted to classify this non-linear data set, right? So as you can see that by default, this is not able to do well on this data set. It's absolutely not clear what the decision boundary is. It's guessing something and it's like wrong half of the time. So what can we do? So if we now add polynomial features here, right? So this is also something that we covered in the course content. So if we add polynomial features to this, then let's say we add x1 squared, right? Now what if we try to learn? Okay, so this is slightly better. Now let's see if we add x2 squared. You can see that if we learn x1 squared and x2 squared, so we scale both of these x1 and x2 to the degree 2. Now we can actually learn this entire data set in spite of having just a linear classifier, right? So, yeah, that is also another way to think about why polynomial features are effective. So, but I mean, think about it for high dimensional data or for very random data, it may not be possible to like figure out what degree of polynomial you want to use. And as a consequence, it is better to just allow neural networks to learn all of that structure and the inherent nonlinearity within it for you. So hopefully that helps you understand the concept of neural networks a little bit and how each parameter roughly affects the output that you get. All the best.